Hey everyone, my name is Taylor Sparks, Editor-in-Chief at Integrating Materials and Manufacturing Innovation. I'm excited to tell you about a brand new paper in our journal. It's AI and statistical mapping applied to additive manufacturing toolpath optimization for wire arc DED. You may not be familiar with wire arc DED, but it's essentially welding that's used to make additively manufactured parts. Here's a diagram from the paper. They show that as you're welding along, you can actually leave behind the bead, and then you could actually use that to build up a material. For example, here they show you how they were actually able to print a flange using wire arc DED. Okay, so the authors remind us that wire arc DED is exciting because it's a way that we can actually produce large components at a relatively low cost. But unsurprisingly, if you've done any 3D printing before, then you know that there's always these different parameters like the power, the current, the voltage, the speed, the step over distance, the stick out, and these are all interrelated, and figuring them out is never easy. They say currently there are no tools available to predict these parameters reliably, so decisions get made based on heuristics, and what we really want is to know what combination of those will give us a nice smooth finish so that we have to do the minimal amount of surface or secondary machining afterwards. Okay. Now there's been some prior work here. For example, Pataniak and Sahu, in their review back in 2021, they did point out that some of these parameters are more important than others. They showed that geometrical features for multi-layer depositions can be most heavily influenced by the step over increment and the bead overlap. But still, there's mostly trial and error to set these. And even when you do build models, for example, using the tangent overlapping model, they found that, okay, 73% bead width is the way to go. Well, a different mathematical model, the parabolic model, shows that it's actually 65%. And then the catch is that these things are all built on specific welding parameters, right? The current and that. And if you were to change those, then these models go out the window. So these are not dynamic models that can't be really used to be arbitrarily used for any weld. And that's what we want to make. So they're going to set out to do that, and they're going to try and do that using an artificial neural network. They think that's going to be flexible enough to learn it for any parameter combination that they attempt. But those readers of this journal likely are aware neural networks are effective at this type of thing if you have the data, but generating, hundreds and thousands of data points is difficult. So instead, what they're proposing to do here is generate synthetic data based off of simpler statistical models on a smaller set of experimental data. This is kind of a cool idea. So let's see how they actually did this. Again, the basic flow is this. They're going to start with 16 samples, only 16, that they collect experimentally. But here's what the trick is. They're going to try and fit data to those 16 samples that they did collect, and then using multiple dependent variables, right? They're going to come up with synthetic data. For example, they're going to do multiple linear regression and statistical mapping to come up with 500 examples of synthetic data, which they will then use to train their machine learning model. Once they have that, they'll measure machine learning model performance against unseen data. Then they build a GUI that people can then use to see how well this all works. So what are these ways of generating synthetic data? Let's take a look at their original data set. Again, here's their first 16 samples, right? You see the travel speed, the wire feed speed, step over, and step over distance as a bead width and distance are their 4 parameters that they are using in their model. Here's the 8 validation samples, which are completely separate, right? These are different values that are not included here that they're going to be validating their model against. When they have a final part, they cut it in the cross section and they measure things like the lower bead height, the upper bead height, the valley height, and then the area of these things. And essentially this can be used as targets for the model to get a nice smooth finish. These are examples of models that aren't working well, where you're getting a large bump here, where they're too close, where they're too far apart. They're getting a little bit better, and then some examples of some relatively nice finishes that are much smoother. They explored both regression model fitting using a bunch of different things like OLS, ridge, decision trees, random forest, right? And they also built models with neural networks and then ultimately measured the performance. And they're looking sort of okay, right? This is on the training data set. On the validation data set, they're testing that against 8 additional sample welds that they've never seen before. So here's what those were and how was their performance. They compare that with what the predicted values were, and they're pretty good. That's sort of the takeaway here. Now, picking which model, OLS, DOE versus ridge, including versus not including dropout, but it was a little bit tricky to tell which one's going to be better than others. Ultimately, one thing I liked about this paper is that they didn't just stop with a trained model, they built a GUI, right? This center is trying to build tools that make it easier to do additive manufacturing and advanced manufacturing. So once they did that, they built this GUI that, and once you select arc welding, you can type in your travel speed, your wire feed speed, and it's going to tell you the appropriate step over distance, which is pretty slick. So check it out in the latest issue of IMMI.